Okay, so we've talked about two transduction mechanisms or coupling of energy between different domains. We talked about thermal transduction, how heat is transferred or managed using electrical signals, producing heat, measuring heat, all those things. And we also talked about piezoresistivity, which is a one-way transduction mechanism. You only can sense some strain in the environment or stress on this, let's say, piece of a resistor, but you cannot really apply any strain or stress through that mechanism, right? So in this lecture, we're going to talk about electrostatic transduction. It's a very, very common transduction mechanism at microscales. We'll talk about the reasons for that by the end of this lecture. But among all these different types of transduction, piezoelectric, piezoresistive, thermal, resonance, all these different types that you have, electrostatic transduction is the most common one, both for sensing mechanical displacements and also to apply forces to these structures. And then we'll see why this is such a popular method at microscales and what makes it so much better at small scales compared to large scales. And after this lecture, we'll talk about piezoelectric transduction, and then we'll touch quickly some of the other transduction mechanisms that are employed at microscales and macroscales in the final lecture for transduction issues. So let's just quickly have a look at what we mean by electrostatic transduction. This is the internal diagram of ADXL 50. It's an old accelerometer. It's one of the first that really put MEMS on the map in terms of commercialization. It's an accelerometer from 90s made by Analog Devices. And then if you open up the chip, the diagram looks like that. But if you want to open up the chip, you will see a silicon proof mass surface micromachined. And this proof mass responds to input accelerations where if there is an acceleration in a certain direction, the inertial force on the proof mass will move the proof mass from its rest position. The proof mass is held in its position by some beam springs. And what we need to do is to measure how much that proof mass has moved from its rest position and then relate it back to the input acceleration. That measurement, the displacement of the proof mass, is done by a set of electrostatic combs or capacitors. So the diagram at the bottom shows you how that works. So once the proof mass goes from here, the rest position, to the right, the finger that is attached to the proof mass becomes closer to a stationary finger, let's say on the right here, and then the gap between those two increases between the moving finger and the stationary finger on the left. And when the gap changes, the capacitance between these electrodes changes, right? So if I measure the capacitance between the stationary finger on the right and comb and the moving one, that capacitance increases, and the one on the left will decrease. That actually gives me a differential signal that I like. Now, and that was the operating principle. But however, there was more than that inside that package, right? So what we did is that we measured how much this proof mass is moving, but it turns out that electrostatic sensing, if you employ it in this sense, is nonlinear. You get a relationship between the change in capacitance and displacement that is nonlinear. So in order to, let's say, reduce the nonlinearity, they had feedback around this structure where the proof mass displacement was measured, and you applied a force to the proof mass to pull it back to the original rest position. That part was also electrostatic. So again, you know that if you have two electrodes nearby and you apply a voltage between them, there will be an attractive force. The two will be pulled towards to each other. All of us have the experience that if you rub a piece of plastic to your hair or something with fur, it's going to attract pieces of, let's say, hay or small pieces of paper, right? That's the attractive force, the electrostatic attractive force. And then in here, we employ it to apply a force feedback to our proof mass to pull it back to the original location. a little bit more advanced than that basic device that I showed is a 2-axis accelerometer, but same operating principle as mentioned in the above. Now, how does electrostatic transduction work? So, going back to basic circuit theory or basic electromagnetics that we have seen in initial physics courses, we know that if you put a charge on a capacitor, if you charge a capacitor with a voltage source, you're going to store electrostatic energy on this capacitor, right? They only store energy, they do not dissipate or waste it. The amount of energy that you store on a capacitor is proportional to the voltage that you apply between the electrodes squared and the capacitance of that device. Now, for a simple case shown here, I have 2 parallel electrodes. The gap between the electrodes is fixed. I assume the portion of the electrodes that see each other has a length of d and let's say width of w, and the separation gap is g. So if that's the case, you can show that the initial capacitance is given by the expression shown to the left, right? So it is the permittivity of the medium between the 2 electrodes times the area of the common, the section of these electrodes that they see each other, right? So if it is a small portion of the overall, you have to look at the electrode, the effective area, not the entire area. Of course, if both electrodes cover each other perfectly, then it is the entire area. So it is the area of the electrodes and then divided by the gap. So that's the formula for it, and again, we've seen it before. And then epsilon naught I'm using here, the reason for that is that at least for microsystem applications, the medium between the 2 electrodes is often just a gas or sometimes vacuum, right? So you usually cannot operate these devices in liquids or across solids. You can, but it's very very rare to see that. So we're going to stick to the common situation where you have air or some sort of a gas or vacuum between the electrodes, and in that case the relative permittivity is almost 1, right? And now if you store that much energy into a capacitor, what happens is that you can go and see if you want to make small changes, if you basically want to remove, to move the electrodes in one way or one direction or the other, what happens to that stored energy, and then how much force you need to make those kinds of movements. Well, then it turns out that if you do the math, the attractive force between the electrodes is given by this expression, right? So in here, the differential operator is going to look at the changes in C, the capacitance with respect to X, Y, or Z directions. So it's a vector operation times V squared. So it's going to be dc over dx, for example, for a one-dimensional situation where only, let's say you have a change in x, it's going to be dc over dx times V squared. The formula shown here is for a more general situation. So that's how you can produce a force. You apply a voltage, and then you get, you look at the dc over dx, or dy or dz, or the combination of them, and you can calculate the amount of force that is produced for that given voltage. On the other hand, you can also look at the change on a charged capacitor, the change in the charge of a charged capacitor when the capacitance is changed due to external forces. So in this case, I'm again having a capacitor. I put a voltage, let's say a DC voltage on it. If the capacitance changes due to external factors, if for whatever reason one of the electrodes moves away from the other one, I have a DC over dt. I have a change in capacitance. And then because of that, I will have a change in the charge stored on this capacitance as long as V is fixed. And the charge on a capacitance is just CV. Traditionally, you ignore DC part, right? So for example, if you go back to your electric circuit course or cases, you had a capacitor in your circuit, you assumed C was constant, and then therefore the charge on a capacitor was just dV over dt. The derivative of the voltage would give you the current. In this case, we are assuming that the voltage is DC, so that dCV over dt, you can write it as dC over dt times V plus C times dV over dt, right? That's the chain rule of differentiation. The dV over dt part, if V is constant, is going to be 0. So what you get at the output is a current that is proportional to how fast that capacitance changed, right? And we can use that to measure the changes. There are other ways. If the changes are very slow, if you're basically looking at DC changes, obviously you don't get a current, but you get a different amount of charge on the capacitor. And we can still measure those, or you can measure the capacitance variation through different interfacing methods. We'll talk about those later in the interfacing section of the course. But the issue here is that, or the point to remember here is that measuring a change in capacitance is electrically possible, right? So you can easily do it with just a DC voltage on this and monitoring the current or charge. And then it's also easy to apply force. As soon as you have a couple of electrodes seeing each other, you can apply a voltage, and depending on how you let the capacitance change, you get a force in the desired direction. So let's look at two situations here. Going back to the same structure, the effective area that I see is of, let's say, length D and width W with a gap G. I'm going to look at two specific cases. Case one, where the electrodes move parallel to each other. So let's say the bottom electrode is fixed. The top one only can move parallel to the bottom electrode. I apply a voltage between the two electrodes. There's going to be an attractive force. But because I don't have any DC over dy or DC over dz, I have removed those two by, let's say, the mechanical setup that I have around the electrode. Those two terms in the equation that we had on the previous page will be 0. The force will be given by that expression. I only have the DC over dx part. Now, DC over dx, well, my capacitance is epsilon dW over G. That's the initial capacitance. If I have displacement in x direction, I can write it as epsilon d plus x, right? X is the change in that x direction times W over G. And when I take the derivative of that expression with respect to x, which is the direction of motion, I just get the equation shown over here. Basically, the force is going to be proportional to the width of the electrodes, inversely proportional to gap, and to V squared as before. So the interesting point here is that the initial engagement of the electrodes doesn't matter. So if they see a lot of each other or they see a tiny portion of each other, as long as you can ignore the fringing fields, the force is going to be the same. You get more or less the same force regardless of the amount of engagement between the two electrodes. So that's really interesting and very useful, as we will see later on. The other situation we can look at is where the electrodes actually move towards each other. So I restrict the motion, let's say, in x and y, and I only let z change, or in this case, y change, right? So x is, let's say, parallel to the two electrodes, z is the other direction in plane, y is normal, right? So again, the bottom electrode is fixed. I can only move the top electrode in up and down motion like that, hold it in place somehow using a spring, for example, apply a voltage between the two electrodes, and in this case, again, we don't have DC over dx or DC over dz because of the way I set up the system. The gap is the parameter that is changing, so I can write it as G minus Y. I know it's an attractive force, right? So it is pulling the two electrodes towards each other. So Y is the displacement towards the stationary electrode. So if I write my capacitance as epsilon WD, which is the area, divided by G minus Y, which is the variable gap, I take the derivative with respect to Y. I can show that I have this nonlinear relationship between my force and displacement. Now, for most practical situations, this displacement, this Y, is much, much, much smaller than G. And if that is the case, you can ignore it and come up with this equation here, what we see here is that in this case, the force is proportional to the area between the electrodes, the effective area, divided by g squared. So this is very, very sensitive to changes in gap. Okay? And again, we'll see how that can help us. In both situations, the relationship between the force and voltage is nonlinear. The force is always proportional to v squared. So let's go through a quick example here to see what kind of numbers we're talking about here, right? So let's look at the electrode situation. We've seen this already a couple of times. And what I want to do is I want to calculate the force in x and y direction. So in one case, I'm going to assume the electrodes only can move parallel to each other. In the second case, I'm going to assume that they can only move normal to each other. And in each case, I want to see what is the force that I will get with these typical dimensions for my electrodes. Okay, so dimensions I have is W is 10 microns, D is 10 microns, and G is 2 microns. So I can quickly calculate dc over dx. So dc over dx will be W over G, remember, times epsilon naught, right? Remember the initial engagement didn't matter. So this is going to be, well, for epsilon naught, for vacuum or gases, it's 8.854 times 10 to the minus 12 farads per meter times W was 10 microns and gap was 2 microns. And if I do the math here, I can see that dc over dx is 44.3 picofarads per meter, right? 10 to the minus 12 meters, farads per meter. I can calculate dc over dy as well. Well, let's just calculate the force here. So if I want to calculate Fx, the force in x direction, it's going to be 1/2 dc over dx times v squared. So the force in x direction is going to be 1/2 times 44.3 times 10 to the minus 12 times voltage squared. And the voltage in this case was just 1 volt. Okay? And if you do the math, it's going to be 22, almost 22 piconewtons, right? It's a tiny, tiny, tiny amount of force, right? Piconewtons. You're talking, even at MEMS scales, this is really not that easy to measure. It's a really small amount of force. Usually we would like the forces that we want to measure to be on the order of maybe nanonewtons or higher. So this is a tiny force. So let's just, this is A. So B, let's figure out how much is the attractive force between the electrodes, right? So in this case, let's write the formula again. So it's 1/2 dc over dy v squared. So I need to calculate dc over dy. And for the normal movements towards each other, so it's going to be epsilon naught, the area between the electrodes, divided by the gap. And I'm going to assume it's a small displacement, so I ignore the minus y squared here. So it's just a small motion. So this is going to be 8.854 times 10 to the minus 12 times 10 micrometers times 10 micrometers for W and D divided by 2 micrometers squared. So because the units for all of these numbers is micrometers, I'm just going to not write it, but keep that in mind. So in this case, you can see that the force is going to be or dc over dx is going to be 221 picofarad per meter, right? And right away you can see it's about 5 times larger, so when you do the calculations for Fy, then you will see a force that is equal to 110 piconewtons. So the force that we get here is about 5 times the force that we get there, right? So right away you have an idea that, if I want to get a large force, maybe the parallel movement, the normal movement of electrodes towards each other, maybe it gives you more force per device area, per chip area. It could be more effective. But something in the back of your mind should tell you that, well, you know what? Don't forget that dc over dy is nonlinear. So yes, you're getting more force, but you're getting a nonlinearity because of the voltage, but also nonlinearity because of the dc over dy part. And maybe you don't like to have so much nonlinearity in your system. It all depends on what you want to do, but maybe that could be undesired. Now, the second part of the question says, okay, so let's go and assume that we somehow make the gap 10 times smaller, make the gap 0.2 microns instead of 2 microns. It is possible, right? So not easy, not trivial, but it is possible. And then as soon as you do that, you expect the forces to go up. But here is the issue. The force that you had for the parallel movement, it's inversely proportional to g, so it is to 1 over g. So you expect that force to go up by a factor of 10. You get 220 piconewtons out of that. That's now a respectable amount of force. But for the device that the gap is changing, well, the change is proportional to g squared. So if you make g 10 times smaller, you get 100 times more force. All of a sudden, you now get 11,000 piconewtons or 11 nanonewtons of force, using more or less the same dimensions for the devices, only a gap that you could shrink to much smaller values. Now, like what we do in CMOS industry, in microelectronics industry, where you have a transistor and you're trying to put the drain of source of that transistor closer and closer to each other, because that gives you a faster device and also a smaller device. A similar race has been going on for MEMS devices, where you're trying to put these electrodes as closely as you can to each other. And for that reason, you get more force out of it. For sensing side, that's also helpful, because remember, the sensing side was also proportional to dc over dx or dc over dy parts, right? So in MEMS industry or microsystem industry, there has been a lot of effort towards making these gaps as small as you can. The challenge here is that compared to CMOS, everything is happening on the surface of the wafer, so the challenge is only lithography. If you can put the drain and source of that MOSFET close to each other and separated from each other after the lithography step, you have solved the biggest problems in your challenge. For MEMS, once you put the two electrodes close to each other after the lithography step, you have to still etch the structure. You have to go into the substrate and create that gap. And that etching step tends to be much more tricky than the lithography step. Lithography, I can get these kinds of gaps easily, but going deep into the substrate and maintaining that gap turns out to be a significant challenge. So, and that is one of the reasons that DRIE is so popular in microsystems technologies. The first reason is that you get these nice sidewalls that make your device well structured and then well behaved, but you also have the ability to create these gaps, these narrow gaps that can go very deep into your structure. Now, as we just saw through that previous example, for reasonable gap values, let's say about a micron or two, you do not get a lot of force per electrode arrangement. The numbers we had there were typical, 10 micron width, 10 micron engagement, 2 micron gap, but you got only about 20 piconewtons of force out of that thing. If you reduce the gap to 1 micron, which is still manageable, you get, maybe 4 times as much more if you move towards if the electrodes move towards each other. So what can we do? That's still a small force even at microscales. So the solution to that, well, I'll let you think for a second. The solution that we just talked about is reduce the gap, but we don't like it that much because it usually means fabrication challenges. The design solution, where you can basically redesign the device in a given technology to do the job you want, is to put multiple of these capacitive elements in parallel. So for actuation side, if you have these capacitors in parallel, now if you look at this structure, you have a capacitor between these. So let's assume the dark gray one is fixed and the light gray one can move in and out for now. So the capacitance that you have will have an element between, let's say, the right side of this finger and the left side of this stationary finger, but you also get a capacitance here. So per finger, per moving finger, you get 2 capacitors. If you have n fingers, you get 2n capacitors, and if the dimensions are the same, you get the epsilon WD over G factor per capacitor. So you can increase your effective capacitance as well as your DC over dx by 2n, right? So you put these guys basically in parallel. It helps you in sensing and also actuation, because what you're doing here is you're increasing DC over dx or DC over dy factors. If the 2 combs move parallel to each other, and in this case you're asking the combs to move in and out. We call these combs for obvious reasons, but they can also move in this direction, and that's a possibility. However, if that's the case, you don't put the moving fingers, you don't put it in the middle of the comb at the beginning, right? So you basically create a gap that, let's say, is smaller in this direction than this side, because if it is right in the middle and this moves to the right, let's say, this capacitance increases, this capacitance decreases, right? So the net effect is very close to 0. So you create a little bit of asymmetry if the movement is, let's say, parallel. The combs are moving parallel to each other, but if one comb is moving in and out, you keep it symmetric. So let's have a look at how this works in practice. This is a device that you've seen before, or a movie that you've seen before. And previously we saw that for the resonant response. Now we'll go back and look at it for the actuators that it is using. And in this case, they are electrostatic actuators. They are combs. And what I'm doing is that I'm applying a voltage to the bottom electrode. Voltage difference between the bottom electrode and the moving part, the shuttle part, will attract the shuttle towards the bottom electrode. If I apply an AC voltage, well, this starts to go up and down, as you can see in the video. Now, one thing that I should remember is that the force was proportional to V squared. So if I apply a sinusoidal signal here, let's say 1 sine omega t, well, think about it as you're watching the video. What will be the frequency of actuation? What will be the frequency of the force that is moving it up and down? And keep that in mind, do that, keep thinking about it. We'll come back to that a little bit later in this lecture. And then, of course, we saw the resonance response, that as we increase the frequency, you see resonance, and that we talked about in earlier discussions. So Now the question are, what are the limitations of electrostatic actuation? Well, we saw that if you look at the normal force between the two electrodes, if the gaps are small, that normal force can be much, much higher than what you could get if the electrodes move past each other. You have a problem here because the dc over dy factor wasn't linear. So if you go back and look at the formulas we had, you could see that dc over dy depends on what is the separation between the two electrodes at this point, right? So that nonlinearity can bother you. But here's the other practical limitation. Well, there are multiple practical limitations. One limitation that you should see right away is that the maximum amount of displacement is basically the gap, right? You cannot go past the gap. So that right away puts a severe limit on how far you can move the electrodes, right? So for that reason, moving towards each other as actuators has a very, very limited range of motion, because you want to start with a small gap so that you get a lot of force. But if you start with a small gap, then the range of motion is limited. However, I have bad news for you. The situation is actually even worse. You don't have that full range of motion. As the electrode on the top, the one that can move, is brought closer to the bottom electrode, you get a larger capacitance, right? And you get a larger dc over dy factor, meaning that you get more force. So this electrode that, let's say you're holding it up with a spring, it saw an initial force of, let's say, 1 nanonewton, came closer to the bottom electrode, but now that it is trying to rest, all of a sudden the force is not 1 nanonewton anymore. Because the gap is smaller, because dc over dy is bigger, now let's say you see 1.5 nanonewtons. So it wants to move a little bit further to compensate for that 0.5 nanonewtons. And then if it moves further closer to the bottom electrode, you get more force and more force. And at some point, the force you get is so large that your mechanical spring that was holding the top electrode up cannot compensate for it. And essentially, the attractive force here will become much smaller than your restoring force, and the two electrodes collapse. This is called pull-in, right? So, and the bad news is that, well, for a parallel electrode situation like what you see here, mathematically you can show that pull-in happens once the gap between the two electrodes is reduced by about 33%. So let's say if your initial gap is 3 microns, you move the electrodes towards each other by about 1 micron. Once the gap is about 2 microns, you hit this instability point, and then the two electrodes collapse to each other, on each other. So you effectively actually have only 1/3 of that gap as your range of motion, and that's, if you push it to the limits, you probably want to have a little bit of safety factor in there. So the situation for a simple parallel electrode is as shown here. So I have a mechanical restoring force. You can show that the voltage needed for pull-in to happen is given by the expression on the right here. Well, it's obviously proportional to Km. You know, if you want to have a larger pull-in voltage, you can use a larger spring. The gap is important, and then of course the area between the electrodes. But nonetheless, the critical distance that you can move is only about 1/3 of that gap. Now, here is what can happen during pull-in in real life. And this is actually well, it was unlucky for the device, but it was lucky for us that, well, in here the researcher was testing this electrostatic device. They're applying a high voltage to it. Everything looked okay. They played with the DC voltage on the power supply a tiny bit, and you'll see what happens if it is running. Yeah. So all of a sudden you see a damage appearing on the top electrode. The situation here is that the two contacted. So this device was operating at hundreds of kilohertz. The video could not capture it. But the two contacted. Once the two electrodes touched each other, you basically melt silicon at that point. You have a high voltage applied to this device, let's say 10 volts, 20 volts, whatever. and you have a tiny contact point, a lot of current goes through that contact point, and you melt the device right there. The reason that I said this was a lucky observation is that usually those kinds of defects happen deep inside the device. So well below the surface, you don't see anything from the top surface. Your device was working just fine. You played with the voltage a little bit, and all of a sudden it looks okay, but it's not working anymore. The reason that it's not working anymore is that something inside that gap has shorted and then basically rendered your device useless. I think this is an exercise for you. You can try it at home and go through these calculations. We already have done the calculation for the force, right, for given voltage and current. The question here is that how much will the gap change if we have a restoring spring constant of 1 newtons per meter. So what we can do is that maybe quickly try to solve that aspect. Okay, so calculation of the force is easy. We already have done that. So F, if the two are moving towards each other, Fy is 1/2 dc over dy v squared. I have the dimensions for the electrodes, and I can go and calculate it, right? So the force is going to be 1/2 epsilon naught. So this is dc over dy factor. It's a square plate. The length squared over g squared is going to be my d squared dc over dy times the voltage squared, which in this case is 1 volt dc. So if you put the numbers that we have here, the first system is a large macro scale system. It's 100 centimeters by 100 centimeters. It's a 1 meter square meter plate held above another plate with a gap of 1 centimeter. And we want to calculate the force. So if you go and calculate the force, it's going to be 44.3 nanonewtons, right? At macro scales, that's not noticeable at all, right? So you're talking about a 50 nanonewton force on a square meter plate. You cannot even measure it or sense it. So macro scale, this is essentially pointless. If I have a restoring force of 1 newton per meter, I can show that delta y that I will get due to that force is just going to be Fy over your k, and that will be just 44.3 nanometers. Again, macro scales, that's a really, really small displacement to see, right? It's only 50 nanometers of displacement. Initial gap was 1 centimeter. So for the macro scale situation, even though these things are happening, we do not notice them, we cannot measure them, we basically ignore them. Case 2 is a situation, I'm going to show part, you can see it on the slides. Case 2, so this is L equal 100 centimeters and G equal 1 centimeter. In case 2, what I do is that I go and shrink the dimensions, everything by a factor of 10 to the 4, right? So I go and get a length of 100 micrometers and a gap of 1 micrometer. Right? So everything, the gap and lateral dimensions, I shrink it by 100 microns. I get a device that is a plate that is 100 microns by 100 microns, sitting above a gap of 1 micron from a stationary plate. In this case, if I go and do the math, I still get, my 1/2 epsilon naught, L squared over G squared times V squared. As long as I apply the same voltage, look at the ratio of L squared over G squared. That hasn't changed. And therefore, I get the same force. Right? And therefore, my displacement will also be the same, because my restoring force is now the same as 1 Newton per meter for the spring. However, this is a huge amount of displacement at microscales. Just for a scale, think about the ratio. This is 44.3 nanometers change in a 1 centimeter gap. This is 44.3 nanometers change in a 1 micrometer gap. It's already 4% of the gap. That is a lot of change. That's easily measurable. And we'll talk about measurement in a second. The last part of the question says, okay, so let's assume that you have these electrodes on top of each other, and each one of them is moving by that whatever displacement that we calculated. It turned out to be 44.3 nanometers. And the frequency of these movements is, again, at macro scale, I use 1 hertz. That's, relatively fast. The two 1 square meters gap, the gap between the two 1 square meter plates is changing at 1 hertz. And then once I scale down the device dimensions to microscales, again, if you go back and look at our scaling lecture, as long as you keep everything linear, your resonant frequencies go up by the same scaling factor. So if I shrink all the dimensions by 10 to the 4, let's assume that the resonant frequency or operating frequency of this device or this movement goes up by a factor of 10 to the 4 as well. So I move these at 1 hertz macro scale, and I move them at 10 kilohertz microscale, and I want to see what happens to the output current that you get. So part C, calculating the output current, so macroscale, you have a current at the output that is dC over dt times V. Remember DC voltage, right? So you will have dC over dt times V plus C times dV over dt. But the dV over dt, V is, so let me just write it here. Or maybe just go back. So this is dCV over dt. This is Q, the charge stored on the capacitor. So I can write it as C dV over dt plus V dC over dt, right? And because my voltage is DC, this term is going to be 0. So I need to calculate dC over dt, and my DC voltage, the voltage that I'm applying between the two, I can write dC over dt as this. So I can write it as dC over dy times dy over dt. Okay? dC over dy I've already calculated, right? So from the section in the above I know that. But dy over dt, so if it is going up and down at 1 hertz, I can write y as the amplitude of motion, so it's 44.3 nanometers in both cases. So let's just call it y naught, some sine omega t, right? Some sinusoidal harmonic motion, I'm assuming here. So therefore, dy over dt is going to be the amplitude of motion that you have times omega times sine omega t. If I'm interested in the value of these, so if I'm interested in I out the magnitude of that signal, it's going to be the voltage DC times dC over dy, which I calculated in the above, times the amplitude of motion times the frequency of operation. Okay? And now I can look at the two cases that I have. So macro scale, so if L is 100 centimeters and G is 1 centimeter and frequency is 1 hertz, then I can calculate I out to be 0.0246 picoamps, basically 25 femtoamps. That's a very small current. That's really challenging to measure, especially because it is at small frequencies. On the other hand, if I go and look at the microscale, where L is 100 micrometers, G is 1 micrometer, and F is 10 kilohertz, and do the calculation, the current that I will measure between the two electrodes will be 246 picoamps, 10,000 times more, right? And why is it 10,000 times more? Well, the DC over dy factor stays the same, regardless of the scale, because I scaled all dimensions the same. V is the same, so the amplitude of vibration is the same. It's the frequency part. The small device can move much, much, much faster than the large device, and therefore the higher. 246 picoamps of current is easily measurable even using a regular general purpose op amp if you're careful. So for sensing side, again, we see that electrostatic sensing is fairly easy at smaller scales compared to larger scales, to macro scales. And this example, the intention behind this example was to show you why we don't use electrostatic actuation or sensing at macro scales that much. But once you scale down the device dimensions, the physics is the same. You just get these scaling factors in your equations that all of a sudden flip the situation, and your micro devices will benefit greatly from those scaling factors if you consider electrostatic actuation or sensing. Now, in conclusion, it's electrostatic transduction is very popular as a sensing or actuation mechanism. They are easy to fabricate. All you need to make is basically a gap between the two electrodes, and that's what we do using etching. You can have lateral or normal capacitors made, and then basically get your displacement vertically or laterally. As long as you can make two electrodes from some materials in your process, you can make electrostatic sensors or actuators. They don't even have to be good conductors, right? In this case, we are basically talking about variations in capacitance. Capacitor values are small. The impedances of these devices are usually quite large, because remember, the impedance for a capacitor was 1 over C omega J. And therefore, the resistance of your electrodes, conductions, all those things don't matter as much. So as long as you have two conductors, and they don't even have to be good conductors, you can have a capacitor. The steady state power requirement is 0. There is really no way for the DC current to go from one electrode to the other, so you do not really consume power to let's say, do the sensing or actuation. And they can be integrated with electronics relatively easily. And the reason for that is that you're not introducing new materials. In electronics, you already have a whole bunch of conductive material, metal layers, polysilicon, silicon. You can use any of those to make the electrostatic actuators or sensors that you want. You don't need to bring in new materials. And for that reason, process compatibility is not an issue. You can make these MEMS devices next to your electronics relatively easily. And in terms of design, you can have symmetric designs. The same design that you use for actuators, you can use it for sensors. The combs that we saw before that improve the capacitance or DC over dy, that increase in DC over dy or DC over dx value helps you both on the sensing side or actuation side. So again, it makes the system optimization a relatively easy compared to some of the other processes. Now, here's an example that I tell you how to solve, but I'd like to go through the solution of this during one of the live sessions. So look at it as a practice problem. What I have is a is an electrostatic resonator, similar to the one that you saw in the movie, right? And what I do is that I have a comb on the left side, a set of fingers that I use to pull these electrodes towards the fixed electrode on the left. So I apply an AC voltage here, and the intention is to pull the middle part or this moving comb towards the stationary comb. And that's what I do. And if I apply an AC voltage, the middle part is going to go left and right. On the right side, I have a stationary comb again, but now in this case, I look at the changes of that capacitance as something that is going to produce a signal for me. So I'm using this comb to move this center part, the shuttle of the device, back and forth. On the right side, I measure a change in capacitance through this DC voltage that I have applied to the shuttle of the device. Device dimensions are given here. The fingers, number of fingers, the overlap, all of that is given. The DC voltage is 50 volts. AC voltage is a 1 volt sinusoidal signal. Quality factor is 10,000. So how do I solve this? The question asks simply, what is I out? Right? You have everything else that you need. The question asks, what is I out under these conditions? A couple of points to remember here. I point them out quickly to you. But here's how you solve it. First of all, go and figure out how much force you're applying to this moving shuttle. And the force, once you calculate it, you can see how much the beam deflects in response to that force. In this case, you have a clamp beam, and the force is applied to its center, right? Because all of that force that is applied to these combs is applied to the center of this beam. So you can think about it as a clamp beam with a center load pulling it to the left. Operation at resonance means that whatever you got for DC is going to be Q times higher. So whatever you calculated at low frequencies under normal excitation, at resonance you get Q times more displacement. And that's it. That's how far this will move back and forth. What is the resonant frequency? You have the effective mass of the system. You can calculate the effective spring constant, and that gives you the resonant frequency. At the output, you do the same thing that we just did for the two electrodes, right? So I out is DC over DT times the voltage difference between the two electrodes. In this case, the voltage difference is this DC voltage here. And DC over DT is you have a amplitude of motion, take the derivative so that you get the velocity, and that's it. Basically, you calculate the output current. The only point to remember here is this. So I just draw the actuator side of this. So you want to find how much force is applied between these two electrodes. So you go and do the calculations. So the force is, let's say this is the x direction, 1/2 dc over dx times v squared. And v is the voltage difference between the two electrodes, right? Now, dc over dx, well, we have that formula for a comb, right? So it is 2 times the number of fingers times the, let's say, depth, if you want, or height of the electrodes, because the initial engagement it doesn't matter, divided by gap. So dc over dy you can calculate. I'm not going to worry about that. Let's see what happens to the v squared part. So I have 1/2 dc over dx times VAC. It's a harmonic signal, so VAC sine omega t, let's say, That's the voltage on the moving electrode, the stationary electrode. The voltage on the moving electrode is VDC. Remember, it is the voltage difference between the electrodes. So it is the voltage on the left side minus the voltage on the right side. And so that's the voltage squared. And then you have to expand this. So if you go and expand that, so let me just use a different color here. So it's going to be 1/2 dc over dx times. You get your VDC squared and VAC squared sine omega t squared minus 2 VDC VAC sine omega t. Okay? Let's move a bit further. So this is going to be your 1/2 dc over dx times VDC squared plus. If you write this, if you go back to your trigonometry, you can remember that, sine omega t squared, you can write it as 1 minus cosine 2 omega t divided by 2. So it is VAC squared times 1 minus cosine 2 omega t divided by 2 minus 2 VDC VAC sine omega t. Okay? And that is going to be 1/2 dc over dx. Again, you can just group the dc components here plus VAC squared. So this is your dc minus VAC squared over 2 cosine 2 omega t minus 2 VDC VAC sine omega t. Okay? So if you look at this term, you have one portion that is happening at DC, one force that is happening at 2 omega, and one force that is happening at omega. So you have 3 forces produced at different frequencies: a DC force, a force at 2 omega, and a force at omega, right? And the question here is focusing on the signal at the resonant frequency. So this is the only component of force that you will take into account. So you look at the displacement because of that and ignore the 2 omega and DC forces in this case. So with that said, you can now go and calculate the force. At resonance, you get Q times enhancement. So with the force, you can calculate displacement of the moving electrodes. Multiply that by Q, you get the displacement at resonance. So it's an AC displacement. With that known, you can get your output current. I have some numbers here for you to check your answers later on. So the resonant frequency is about 52 kilohertz once you calculate it. The displacement at resonance is 2.1 micrometers, right? So off resonance, you do the calculation. And at the end of the story, the number I have here for I out is 150 nanoamps. So go through this problem, the rest of this problem in your own time, and we can discuss it during the live sessions of the. Now, for the rest of this lecture, the remaining few slides are about the applications, cases. So electrostatic actuation and sensing is very popular, as I mentioned before. And in this case, you see 2 different devices. So there is ADXL 202 accelerometer. This is a 2-axis accelerometer. It gives you acceleration in X and Y directions. And you can see that, here is your proof mass. This is your spring. So you have your mass spring system. And these are the electrodes that we use for detection of the displacements. And in this case, you can see that we have 2 stationary electrodes and 1 moving electrode. If this electrode moves, the moving electrode, let's say, moves to the right, the capacitance between these 2 increases, the capacitance between these 2 decreases. You can use differential sensing. This is an ADX-RS 150 gyroscope. You have 2 electrostatic resonators in this case that actually work in tandem, and then you can detect the Coriolis force due to the angular rate using that device. But the actuation for the resonators is electrostatic, and measurement of the displacements due to the Coriolis force is also electrostatic. Here is a strain sensor, a strain gauge that uses a capacitive interface. So in this case, the 2 ends of these structures, one of them at least can move, and once they move, they push the electrodes into each other, they push the combs into each other, you get an increase in your capacitance as this end is moved away from the other end. Here's a capacitive microphone. In this case, what I have is a large plate here and a stationary plate right below it, right? So that forms a capacitor. The top plate moves up and down in response to the variations in acoustic pressure, right? Or to acoustic signal that is coming in as a wave. And that changes the capacitance between the 2 electrodes, which you measure as an indication of sound intensity. The membrane is held up using beam springs at the edges. You want a relatively soft membrane. And finally, this is the device that we have made at SFU. It is one of the accelerometers that we developed actually it took us several years to get here. But the device is fantastic. It has a 5 kilohertz bandwidth and a noise of 250 nanoG per root hertz. The sensitivity of the device is 1 picofarad per G, meaning that it's a capacitive device. Once you flip it, you get a 2G signal, and then you get 2 picofarads of change in capacitance. Here is how it looks like. So we have some springs. This is a very rough schematic of the device. And once you have acceleration in this direction, the gap between these electrodes changes, and that gives you the signal for measuring the acceleration or estimating the acceleration. A package device looks like this. For a MEMS device, this is relatively large. It's about 1 centimeter on each side. With electronics, it looks like this, and the performance of this device is basically outstanding. It's been a few years since we made and published these results. There hasn't been any device that actually even close to this device. We have less than half a micro G of noise here and a bandwidth of 5 kilohertz. There is nothing out there that can meet these 2 specs put together. And that's it for the electrostatic actuation and sensing or transduction mechanism. The next lecture will be about piezoelectric transduction, and then we continue to other less common transduction mechanisms after that. Thank you.